Chapter 6, Lesson 3 of Advanced Algebra, and we spent the last few lessons working on dividing these polynomials, these higher degree polynomials, third, fourth, fifth, sixth, seventh degree polynomials, and we've been dividing them. And we talked about at the beginning of why we do that, what's the point, a little bit. We want to talk a little bit more about that moving forward because there is a theorem that we're going to talk about that can help us determine what it is we're trying to determine by going through this whole process. And that may sound a little bit confusing, so let me try to straighten that up for you. We've talked about wanting to know what the factors of a polynomial are because you remember if we have all the factors lined up and we put them equal to 0, those factors allow us to determine what the zeros of the function are. And those zeros, those points where it crosses or touches the x-axis, are very important points both when we're trying to graph those polynomials, or if we're applying those polynomials, those points become very important points in the data that we're looking at. So being able to determine where those zeros occur is very important. And knowing what the factors are allows us to determine what those zeros are. So it's important that we have a way to determine what the factors of a polynomial are so that we can determine what those zeros are. Now, when we looked at quadratics, it was kind of easy because a lot of the quadratics factored. We talked about factor by grouping and special factoring things, and quadratics that factored allow us to get it into factored form pretty quickly, which again allows us to determine those zeros. However, with these higher degree polynomials, the factoring isn't quite as easy, and sometimes it's not even possible. So we need another way to do it. So division is one way to do that. And again, we want to divide because if we know what the factors are, we can determine what the zeros of the function are. And again, the zeros are important because that's where we know the graph crosses or touches the x-axis. Now, we know that we have a factor when we do division, we get a remainder of 0. Okay, so when we go through the whole division process, the reason we do it is we want to know what the remainder is, because if the remainder is 0, we know we have a factor, which we can then figure out the 0 from. And if the remainder is not 0, then we know that that's not a factor. Okay, so what do you think would be nice to know before we even started to divide? Wouldn't it be nice to know what the remainder is going to be before we go through the whole process of dividing? I mean, wouldn't it be nice to know that this is a factor because I know I'm going to get a remainder of 0 before I even go through the whole process? That would be nice to know. And actually, there is a way that we can know that. If we know that the remainder is of 0, we know it's a factor. We know if the remainder is not a 0, we know it's not a factor. Also, if we know what the remainder is before we start dividing, then after we do the division, we'll know if we get the remainder we're supposed to get, we'll know that we did the division correctly. If we get something different, then we know we've done something incorrectly. So knowing what the remainder will be before we begin to divide would be a nice thing to know. And in fact, there is a way that we can know it, and it's called the remainder theorem. And the remainder theorem says, if you have a polynomial of a degree that's bigger than 1, and you're going to divide by a 0, where a is some constant, then the remainder is going to be p of a. Now what does p of a mean? Remember, p of a means you're going to substitute a into the function. So if you have this polynomial function and you're going to divide it by this linear factor, you can determine what the remainder is going to be before you do any division by simply taking the number here, a, putting it into the function and simplifying it, and the number that you get is going to be your remainder. Now again, it has to be in this form, x minus a. So we can substitute the 0, whatever the 0 would be, into the function, and the value that we get will be the remainder that we should get when we divide. So let me show you an example. So let's look at the example we did earlier, where we had x cubed minus 5x squared plus 3x minus 2 divided by x plus 1. Now, what we would like to know is is x plus 1 a factor of this? And we did the whole division process, and we found out that it is not a factor because we got a remainder of negative 11. So wouldn't it be nice to know that before we did the division? Again, we would know if this was a factor, number one, and we'd also know, have a way of checking our division to make sure we got it right, because we would know what the remainder is going to be before we even divided. So the remainder theorem says if I take the zeros, if I take the negative 1 and I substitute it in for x, that means if I do p, let me do white here. If I do p of negative 1, meaning I put in negative 1 for every x, so that's negative 1 cubed minus 5 times negative 1 squared plus 3 times negative 1 minus 2, and I simplify this, the value that I get is going to be my remainder. All right, well, let's test that out. So negative 1 cubed is negative 1. Negative 1 squared is 1 times negative 5 is negative 5. Make sure you do PEMDAS. 3 times negative 1 is negative 3 minus 2. So this is 5, 6, 7, 8, 9, 10, 11. That indeed does give me a negative 11. So my remainder is going to be negative 11, which is what I got when I divided. So using the remainder theorem, I can figure out what my remainder is going to be first, which tells me this is not going to be a factor, but then when I go ahead and do the division, I can tell what my remainder is going to be before I even start. Okay, so that's the remainder theorem, all right? And so we can use that to help us out when we're doing these division problems, all right? Now, I'm going to go, let's go and look at a few of those division problems that we've done already. We've done long division and we've done synthetically, and let's look at see if we can't figure out what the remainder is going to be before we even divide. All right, so let's see my remainder, what my remainder should be. So I'm going to divide by p minus 1. Let me get this down a little bit. So if I take negative 1 and I substitute it in for p, that should tell me what my remainder is going to be before I do any division. So let me plug negative 1 in for all of this, and then let's go ahead and do that. So negative 1 cubed is negative 1 times 5 is negative 5. Negative 1 squared is 1 times 2 is 2. Negative 8 times negative 1 is positive 8 plus 1. So this is 8, 9, 10, 11. Negative 5 plus 11, which is positive 6, which is the remainder that I got. Okay? So let me do one more. Again, this is the remainder theorem. I can determine what the remainder is going to be as long as this is x minus a again. So it's a restriction, the same restriction we had with synthetic division. And then I can figure out what the remainder is going to be. So this one's going to be negative 5. No, I'm sorry. What makes that 0 is positive 5. So this is going to be 5 cubed minus 3 times 5 squared minus 9 times 5 plus 2. Now, if you remember, you can use your store key on your calculator, store this value in as 5, and then enter this in and do it a little bit quicker. But I'm doing it by hand. So 5 cubed, 5 times 5 is 25, times 5 is 125. And then 5 squared is 25 times negative 3 is negative 75. Negative 5, that's negative 45, and then plus 2. So this 125 and this positive 2 is 127, and this is going to be negative 110, negative 120, right? Okay, and then we subtract that. That gives me a positive 7, which is the remainder that I got when I did my division. Okay, so I'll do one more example of the remainder theorem, and so you can see how that works. And then again, make sure that we only use this for values where the divisor is in the form x minus a. So let's do this one here. Again, the 0 is negative 8. So if I substitute in negative 8 into my expression here, then I'll be able to determine what the remainder is going to be before I even start. Now this one I'm going to need my calculator on, so let me try and find it. Oh, here we go. It's hiding under my textbook here. So if you remember, I'll try to show you here, but on your calculator, if you use the store key right here, we can store that negative 8 as our x value, and then I just have to enter in the expression, and it will give me the answer. So I'm going to do negative 8, and I'm going to store that as my x value, and then I'm just going to enter in the polynomial. So I'm going to have 3x cubed, let's see, 3x cubed plus 26x squared plus 10x minus 51, enter, and I hit a negative 3, and as we see, that is what I've got when I did my division problem. Okay, so the remainder theorem allows me to determine what the remainder is going to be before I do my division, and again, it gives me two pieces of valuable information. Number one, it tells me whether this divisor is going to be a factor or not. A remainder of 0 says it is a factor, anything else is not. So this is not a factor. And it also allows me to know what the remainder should be so that when I do my division problem, if I don't get that number, I know I've done something wrong. Okay, so that's the remainder theorem, a very useful theorem that we'll use quite a bit moving forward.